Okay, Mick, I guess we could probably start. I'm very grateful to you for participating in this exercise.
Well, Archie, I count it as a great honor. I think we've probably worked together actively for pretty close to 35 years. And since retirement, of course, we've kept in touch over all this time. And the progress in electron microscopy has been stupendous. I mean, it is the most amazing development, really. I don't know, how do you want to start?
Well, probably start at the beginning when I was incredibly lucky to come to Cambridge to work with Peter Hirsch back in 1957, and it was pure luck. I mean, I got my first degree in Edinburgh in physics, and then had a year at Caltech, sitting at the feet of Feynman and Gell-Mann, which was a great experience, of course. But I didn't think that was really for me in the longer term, and I then wrote to Mott, and stimulated by an article by Mott in Nature about measuring the Fermi surface. I wrote to him asking if it would be sensible to come back to the UK and either do a PhD or work in industry, as a strange letter. And I now realize, of course, he just regarded that as a straight PhD application. And eventually, I got a response offering me a couple of opportunities, either to work on the Fermi surface with people like Pippard and Schoenberg, or with Hirsch on this new method they'd found of seeing dislocations. And it was really rather lucky that in the solid state course at Edinburgh, the word, unusually for a solid state course, dislocations had actually been mentioned by a man called Arthur Brown. And so I knew about dislocations and decided I would go for that one.
Well, I'm sure that was the right decision. What else can I possibly say? I must say, I think I was even luckier than you, but much less well educated, because of course Hirsch had a grant going from the Admiralty, and he had to find somebody to fill it. And so when I finished my PhD in Birmingham on physical metallurgy, basically deforming rock salt, he needed someone to fill in for a year or two in his grant. So I was, what shall I say, a bit of Chinese checkers out there I was, and was the beginning of the most wonderful experience. And of course, we met almost immediately, I think, because I was trying to learn electron microscopy, which seemed to me suddenly all this speculative stuff about dislocations, with all respect to Arthur Brown. I mean, suddenly you had the power to see them, to understand them, and to understand quite mysterious and important things like work hardening, fatigue, and so on. That's what drew me. Well, I wonder, maybe could start with, I mean, one of the puzzles I had beginning was to understand what was meant by diffraction contrast. I found that extremely difficult to understand. So who and how did that term actually come about?
Well, I must admit I'm not quite sure. I suspect it must have been Peter Hirsch's term. Thinking about it, of course, what the main nub of the matter was that electron diffraction on its own by that time was really struggling compared with the tremendous success of X-ray diffraction. Electron diffraction was hampered by the multiple scattering dynamical effects. And so interpreting structures straight from diffraction was very difficult, electron diffraction. And so adding the microscopy was absolutely crucial. Now, it could have been called perhaps diffraction imaging or diffraction microscopy or something. I think the other aspect was that, of course, electron microscopy was quite a well-established subject by that time, but it was entirely based on the idea of contrast arising from stopping power or mass thickness.
Yes,
The idea of the electron being a wave was not part of this picture. And so that was perhaps the diffraction contrast was a term perhaps to be compared with mass thickness contrast.
Yes, yes. But it encapsulates the main point that it's an imaging technique that's sensitive to the local orientation that the electron feels as it traverses the crystal, which was really the clever thing. And once certainly I found it much suddenly grasped that fairly early on, and it's a terrific. It's quite interesting, isn't it? The crystallography group, which was Peter Hirsch's group, I think, at the time, really taught quite sophisticated understanding of diffraction. I had never heard of reciprocal space, the Borman effect. I had only a most elementary knowledge of crystal structures and the Bravais lattices and things like that. Maybe even sub-Cattell, I would think, at that time. How did you come to this rather technical side of what was then X-ray diffraction?
I think it really all came from Peter Hirsch rather than from the crystallography group. The crystallography group set up originally by Bragg, and of course, still in our time, coming from its tremendous success with large molecular structures like the DNA and so on. It was an enormous group of people. It probably was more than 50 or 60 people. And within that, there were a number of subgroups. There was the MRC group looking at these big biomolecules with Crick and Perutz were still around. And then there was a group looking at clay minerals.
Yes.
With W.H. Taylor and then Cochrane was still around, I think.
Yes.
And then there was this small group, Hirsch's group. Hirsch himself knew a lot of crystallography and things like the Borman effect, but the rest of us nothing. And in fact, it was really strange. There were occasional get-togethers of the whole crystallography group out at coffee events out at Girton, run by Lynn McGaw, where there would be lots of short talks of the order of 40 talks, each lasting 3 minutes.
That's right.
And we were at one extreme. There were these people with their, what they called their R factors, which were the extent to which their data fitted the model or something, with enormous unit cells. And we were never getting, we got past simple cubic. We were working with face-centered cubic and body-centered cubic, just occasionally the diamond structure. That was the limit of ours. So there was really very little overlap.
Yes.
And then the specific Borman effect thing was, I really wonder whether people like Crick and Watson, they would know anything about the Borman effect. It was Hirsch knew about it.
Yes. I still remember the cackling noise of Crick's laughter in the coffee room of the old Cavendish, which was where a great deal of communication took place across these group boundaries and subgroup boundaries and so on. Very, very important. Well, now pivoting neatly, your first job was to grow a single crystal, as I understand it, and you have a photograph in I think your first slide or one of your slides shows, making a carbon mold and so on, a graphite mold and so on. And it's a pretty difficult thing to do. And the fact is you succeeded. But the question I have to ask you is, was it worth it really?
Yeah, well, it was a big learning experience. I got put onto that project, right? I was originally supposed to look at radiation damage, but then I got independently a research studentship from Trinity College, and that made money because Peter Hirsch then could shift his money. And so John Silcox came to look at the radiation damage problem.
Right.
And I was then told, you'll study the work hardening in single crystals. And so that my first task was to grow a single crystal. Yeah. There'd been an earlier student Mike Brett, who grew single crystals of gold, actually, and deformed them, but didn't do any electron microscopy, as far as I remember. Now, a big problem, in fact, was at that time was to get thin sections from a bulk material, which was mostly done by electropolishing. which was a terribly tedious technique and even dangerous.
Yeah.
And so to make the electropolishing easy, I thought that I have to grow these single crystals in the form of flat plates, maybe about a millimeter or so thick.
Yes.
And in fact, Brett had used graphite molds, but he was working with quite cylindrical crystals with it. And so I redesigned these molds, graphite molds, to suit flat plates, and I rapidly found that they're really a nightmare thing to machine in the lathe and milling machine and so on. You get tremendously dirty. The workshop staff rebelled and refused to do it, and I had to do that myself.
Yes.
People may find this a bit hard to believe, but and so in a sense, I'm quite proud of these molds. In fact, I redesigned the mold to make the machining a bit easier. I found that pretty quickly that I was fighting surface tension.
Yes.
I mean, I suddenly realized when I opened up the mold, first of all, it was filled with little globules, spherical globules of copper, which reminded me immediately of the mercury when you pour it around. I suddenly realized that surface tension is a serious problem. And so I had to redesign the mold so that there was quite a lot of pressure. It was held vertically. And I did succeed in growing these crystals. And then an extra dimension was added usefully by getting together with Peter Swan in the metallurgy department.
Yes.
They had a facility to make alloys, and we had copper, aluminium alloys of different composition with different stacking fault energies. That was one of the crucial parameters.
Yes.
And I got a few pictures of these, one of which was shown. And the main impact of these pictures now on me is that I find it very difficult to understand what you would see if you looked at a structure like that by high resolution electron microscopy.
Yes.
The diffraction contrast method is fairly important for that kind of thing.
Yes.
But you're quite right. The thing that was pretty much the end of the story as far as I was concerned. It didn't finish because my first research student, nominally mine, but actually looked after guided by Peter Hirsch, was John Steeds. And John Steeds immediately went to town with the thing because, well, first of all, by that time, they had spark machining and various ways of cutting a section from a bulk crystal. So he could work with pencil-shaped sort of crystals, deform them. And then secondly, maybe even more importantly, Ugo Valdre had come along with his goniometer, tremendously elegant design, which enabled you systematically to tilt to different Bragg conditions and identify all the Burgers vectors.
Yes. The design based really on the biro pen in a way, a bowl. Yes, no, it's a wonderful thing. Of course, we're going to come back to the radiation damage, but there is a comment. The work hardening structures, even with single crystals and all this very, very complex crystallographic, even for the simplest ductile materials like FCC and BCC, they are very complicated structures, and there's both. They're mesoscale structures, but they extend to the atomic and the stacking fault energies and the core structures. Then they extend all the way back up to many microns, millimeters even. So it's a very difficult problem. And then there was the battle with Zager, which it's very hard to imagine putting research students into the no man's land between Hirsch and Mott and Zager. I think that, what shall I say? Your picture of that's a copper alloy you have, the one that comes from the thesis, I think, right? It stood the test of time, I would say, really. I mean, it's the start of something really very big and very complicated. One thing that struck me again about the Cavendish at that time, the Howie-Whelan equations, perhaps come back briefly again to that, but I mean, the Cavendish had very superior computer facilities. Many staff members, however, were very skeptical of computation. I do remember Neville Mott's attitude was really somehow a bit sniffy about actually doing numerical processing of these equations, but it was extremely important to have these detailed computational comparisons between the theory and experiment, the imaging experiment. So can you remember what the computing facilities were like at that time? How much did...
Well, the computing facilities they weren't in the Cavendish. They were in there was a separate computing department. I don't remember what it was precisely called, but run by Maurice Wilkes, who was a great pioneer of computing. And so I think that Cambridge at that point had one of the best computers in the world. Not only the hardware, but the software was tremendous. There was all kinds of subroutines available at that time, which I don't think were available anywhere else. We were quite unaware of how we benefited from it at the time, and you simply had to go. You didn't have to get Mott's permission. Whelan, I don't know whether it was me or Whelan, realized that we should make use of this to calculate this, to apply the Howie-Whelan equations. And the only thing you had to do was to go along and see a great guru called Swinnerton Dyer.
Yes.
And tell him about your problem, and he would. There were three possibilities: either he would solve it himself on the back of an envelope, or he would tell you it was ridiculously beyond the capabilities of the machine, or else it would be okay. And fortunately, we fell into that third category, and it turned out to be the great thing that for quite a few years anyway, that was the way to proceed. We didn't do what would be done nowadays, market a computer package, partly because we were working in some kind of far from universal, almost machine language to write the things.
Yes.
But so it was really just a question of explaining to people how you went about this integration, and gradually other groups did it.
Yes. Of course, the crystallography group was indeed a very big user of computer time.
Yeah, sure.
They were taking up huge fraction of the time, so you found yourself as a small component really of that. So I suppose it made it a bit easier. Well, it's very interesting. I think about the Howie-Whelan equations. I've always somehow myself, I was really so impressed. They seem to me to be more or less as effective as Maxwell's equations. Perhaps that's overstating it a bit, but the fact you could compute images and learn things and feel yourself on concrete ground. The thing that I had most difficulty grasping about them is the use of complex numbers in them, because there's sort of two different uses. One is to do with the absorption effects, and the other is the propagation effect. The I pi over psi g or whatever.
Yeah.
And so that was what I found hard to grasp, and eventually I guess I did. But I mean, how did those equations come about?
Well, I think they coming about in the mind just to write them down. I think that was not so difficult. I think we realized that. I think Hirsch, we could see there was something not matching about the computations and the images when we first ran them. And Hirsch was the person who mentioned this Borman effect. And so it was clearly some kind of absorption effect that the electrons, which were mainly channeling down and hitting the atoms all the time, they were being scattered out of the beam, so it looked like absorption.
Yeah.
So the standard way to take account of that is to make a potential with an imaginary part.
Yes.
And so that was sort of reasonably straightforward idea. And then we just fiddled around with how big should we make the imaginary part to make it look like the observations.
Yes.
And I can't remember now the detail of how you did the actual algebra, the computations with numbers with real and imaginary parts. I've got a feeling you just, when you multiply them together, you just slug the whole thing out in the usual way.
Yes, I think that's my memory too of that point. Yes. Well, I mean, you not only getting the stacking fault energy with Peter Swan, and that's had a tremendously influential, long-standing effect. where you say it reconciles electronic properties and crystal properties. I still think it's probably way ahead of any electronic modeling, really. I don't think there's been, maybe apart from aluminium, the sort of modeling that makes you feel really confident, especially with alloys, but anyway, that's an absolutely pivotal result in my opinion. But now we come to the plasmons. I mean, from my background, I had no idea about plasmons. They seemed, they sort of partly came out of the Maxwell equations, and partly you could sort of visualize a simple capacitance with electrons sloshing backwards and forwards. But the fact that would conserve contrast, now I seem to remember we had lots of group discussions throughout all of this. May I say, I think we had a superb group, and we had easy, not so easy, well, sometimes not easy, but we encouraged genuine discussion. And I do remember heated discussions about the conservation of contrast using plasmon scattered electrons. I mean, the plasmon scattering angle is very, very small. I make it to be about 1/100th of a Bragg angle. It's like a kind of tiny enlargement of the incident beam or something. But I do remember having extraordinary discussions. Supposing the plasmon scattering came before the elastic scattering, then you would expect contrast to be conserved, because it's just as if the incident beam had got slightly wider. But supposing the elastic scattering came after the plasmon scattering, well, you would expect the same thing, because you'd just be collecting slightly different. They didn't have much to do with the contrast. It just had to do with a very, very residual blurring. So and that all seems incredibly naive, because the notion that one would come earlier than the other is ridiculous, isn't it, really? So
yeah, probably is. I think I think in some ways it's one of the things I'm proudest about, because it was a sort of one place where the electron microscopy contributed something to physics.
Yes.
If you look, there's many books, if you look at them in branches of physics, will state that interference is killed by inelastic scattering.
Yes, that's right.
Which is certainly true in a case, because you cannot get two waves with different energies and therefore different frequencies to provide a static interference pattern.
Yes.
But of course, that's not what we're asking. We're just saying the inelastically scattered electrons on their own can interfere, each one.
Exactly.
So,
yes.
And it just inherits the phase in the quantum phase transition matrix element. It just inherits it. Nevertheless, it has still an ongoing subject of discussion. I mean, the driving force right at the beginning was simply the fact that the specimens we were using were 2 or so mean free paths thick, mean free paths for exciting plasmons.
Yes.
And so every electron that came out of there had probably lost 2 or so plasmon.
Or at least one. There were multiple.
But showed all this incredible contrast. And of course, and that was shown much better than the data we had by when Castang, who had his group in Paris, had proper electron spectroscopy equipment. And they had images where you could not tell the difference between the zero loss and the plasma loss.
Yes. Sure.
And so there was an incredibly strong experimental signal that we would actually write about this. So that's what occurred. And so you just had to have a theory that actually produced it.
Yes.
But it's still a subject of discussion. I mean, there's still debates going on about in cryo-electron microscopy, fantastically fashionable topic right now, of course, the possibility that you could get a little bit more use of the electrons you've fired at the specimen by making use of the inelastically scattered electrons. Which is important, because there's so much beam damage going on. They have to make use of every electron.
Yeah, absolutely. No, I think we'll come back to that.
So it's slightly revived again in that context. I'm not sure it's going to help a great deal, but
yes, it should be a marginal effect, of course.
Their specimens are much. That's one of the main points, is that of course nearly all of transmission electron microscopy has moved to much thinner samples.
Yes,
and so the plasmon scattering is not a dominating. It's there, but it's not swamping everything else. So
yes,
it doesn't attract so much attention.
Yes, that's
Not
certainly.
not in terms of the images anyway.
Well, in terms of yes, I'm going to just jump slightly, I think. I mean, I think you kind of overestimate the degree to which diffraction contrast has been outmoded. There's still a huge amount of work. I mean, it's a question really of whether you, as I think you probably do, you regard electron microscopy as really a branch of physics where you can see the development of the technique in the context of physical ideas. But there's still a huge amount of work going on in which it really is an instrument for improving alloy design. I'm thinking of key areas like superplasticity or alloy development in Birmingham, the titanium alloys being developed with Jones and Loretto. I mean, electron microscopy plays a central role there, and it's all diffraction contrast. So I think that, as it were, the view the view from the Cavendish might be slightly distorted in terms of the Yellow Book still sells, doesn't it?
I don't know. We don't get any money from it.
Don't get any money from
No, I don't know whether the Yellow Book. I mean, no. The Yellow Bible's been totally overtaken by
by
Carter and Williams.
several other books,
Yeah,
several, including Loretto, Jones and Loretto and so on. Yeah, sure, absolutely. Well, I think you're slightly, well, getting now back to the sort of physics and the sort of atomic contrast and so on. I think the multiply twinned particles were a tremendous surprise, certainly to me, and I think that's a genuine discovery, don't you think? Wouldn't you?
I don't think, to be honest, we can claim to be the first to have seen multiple twin, but it came out. Laurie Marks, who was one of my research students, who had money. There were things called case studentships, money that where industry was involved. They didn't actually provide much of the money, but you had a project jointly with them, and he was with ICI looking at catalysts. And when he looked at this thing, there were these. Actually, rather, they weren't all that small. They were pretty ginormous multiple twins, and of silver, I think, if I remember rightly now, and they anyway. It was a note in Nature, and this was a fascinating. At one point, we naively thought, "My God, these are the real key to catalysis. You've got to look at every catalyst and find out how many multiple twins are in it."
Because it exposes a particular surface, yes.
And then, of course, where things were much more original, what Laurie did was he worked out with Wolff's theorem, looked at the real surface structure in it's not, there are dents where the faces meet. And then even more, people, I think, previously had realized they're internally strained because there's a gap when you count up the angles around the thing. There has to be some elastic strain. But I think the advance we made with the help of Elizabeth Yoffe in the group was it's not a uniform strain. It's quite an interesting function of position in the particle.
Sure.
And so in principle, the columns of atoms are not necessarily straight. They're bent slightly. I still think they're still looking for that, but it's got to be there.
Yes, sure. Yes, the trouble is to get them in the right orientation, I expect. Yes.
And then the other thing I should mention, I think, is that that it was mainly Dave Smith and Laurie Marks who Dave Smith had got Coslet's high resolution 400 kilovolt microscope really working, and for about a couple of years they had the highest resolution electron microscope in the world, I think, and got some marvelous pictures of these multiple twins.
Yes, they were particularly interesting because a lot of the very high resolution pictures that were exciting at the time were really just interference patterns of crystal structures. The definition of resolution was, it's not quite right, it seemed to me at that time, whereas the multiple twin particles actually had structure and you were seeing something real, as it were. Then we now come on to the high angle annular dark field, and of course the STEM came with a crew type detector, but we it was really very disappointing. And I must say that your recognition that you had to, when you're in the crystal, using it for crystals as opposed to amorphous materials, you really had to get rid of the Bragg the diffraction contrast with the which had become an enemy rather than a friend. And I always tend, it's a bit of a joke, but I think that HAADF possibly means Howie's adaptation of annular dark field, because I think you must have had the insight really to see that that's what had to be done to the detector to make it work. So what's the story behind, as you see it?
Well, I don't think I was really totally conscious of all the factors that I now think were relevant. But one of them, of course, was that Crewe had already distinguished between the high angle and the low angle scattering.
Oh, yes, absolutely.
I don't think Crewe was one of these basically nuclear physicists who didn't much believe in the electron as a wave, and so he was just distinguishing between the small angle inelastic scattering and the large angle elastic scattering. And the extra point that we realized when we realized we're fighting crystallographic contrast, the catalyst particles couldn't be seen because of all the crystallographic contrast coming from the support. We had to suppress somehow that, and that was the point when I remembered I should now mention my second research student that was again basically working with Peter Hirsch was Chris Hall. And Peter Hirsch again remembered that there's a standard thing in X-ray diffraction. You can separate out as a function of angle the scattering into coherent, which is from an atom, it's just the atomic structure factor squared times the Debye-Wöhler factor. It gets reduced at higher angles because of the vibrations. But we know the atom is actually scattering the full F squared. This is in one of the slides. And so you can, using the Debye-Wöhler factor is a measure. If the Debye-Wöhler factor becomes less than a half, that tells you that most of the scattering is incoherent, diffuse. And therefore, that was the simple criterion. Go out to angles where the Debye-Wöhler factor is about a half. So that means bigger angles.
Yes.
And then, of course, it was a really lucky break, thanks to our research students, that we couldn't actually get to such a big angle with the detector outside the cartridge of the specimen cartridge. We had to work inside, and it turned out that Steve Pennycook had the basis of a detector to do that for cathodoluminescence.
Yes, that's
right. They realized it wasn't anything to do with me, or I don't know you either, but he and Mike Tracy, somehow cooked us up and succeeded in getting these high-angle dark field images.
I certainly think that the tapered tube, Stephen Pennycook's tapered tube for getting the cathodoluminescence to essentially be focused was one of the key and very lucky strikes. I mean, one of the strengths of our group, I think, was there's enough communication and enough flexibility with the postdocs staying around for a bit that one can make steps in that direction. It's a great deal stronger than just a man and a boy, of course. And coming back a bit, in the early days of the STEM, there was all this business about STEM was supposed to improve penetration, and suddenly a 100 kilovolt machine would give you the penetration of 500 kilovolts. And that was floating around, and Mike Loretto proved conclusively that it wasn't. And of course, there was this confusion between, you could see the high contrast images from the top couple of layers of a film, and then it would get blurred by the stuff going on beneath it. But the STEM, if you call that penetration, yes, okay. But basically, people had forgotten, really. And this comes back, I mean, in one of your slides, you show the thermal diffuse scattering as very, very small. You show what happens to the contrast with the inelastic scattering as a function of thickness. And the thermal diffuse scattering is very small, but when it comes to using those high order reflections, in something like tachography, the thermal diffuse scattering plays a considerable role. So, I mean, there must be still quite a lot of work to be done in that area, I would think.
I'm just trying to think. I think the slide you're referring to is the one where to do with the weak beam imaging. We
It's the Tiba guy, I'm thinking.
Yeah, we tried to.
Yes,
I mean, I still think there's some possible mileage in weak beam imaging, in that the weaker and weaker the beam you go to get the diffraction contrast image, the
yes,
sharper the images can be,
indeed. Yes, yes,
and ultimately you get limited by the signal to background.
yes,
There's a background noise from inelastic scattering,
yes,
large angle inelastic scattering, in fact, and we made a crude measurement of that. We didn't have a spectrometer to do it properly. We measured it, and it does seem that with the kind of energy filtering equipment we got now, that could be revisited, and much weaker, much sharper weak beam images could be obtained. But
I certainly agree. And I mean, what do you think about really making a go of cooling the cartridge and doing
yeah, that's it. Yeah, sure.
must make a huge difference at the
But I think the main problem with any of these ideas now is that the average electron microscopist is equipped with some very sophisticated aberration corrected, God knows what electron microscope, and it's not easy to do these things anymore. I mean, it's far from clear how to. I mean, I remember, stimulated a bit by John Spence. I did have one of his people. We joined together for a belated weak beam experiment, and it took quite a long time. First of all, to explain to the student what the heck it was we were asking him to do, and secondly, actually to do it in the equipment. It's not so easy now.
Yes, that's true. But it's also true that one of the advantages of STEM is just that it's much easier to control and
Yeah,
understand what's going on than it is with the modified
yeah.
TEM STEM machines. Well, let's get back to another term which has always struck me: aloof, ALOOF, right? I think I first heard you use that in a seminar, and you must have, did you think of that, aloof?
No. I think that
But,
came from Rufus Ritchie. I mean,
oh, really?
Rufus
Oh,
Ritchie, of course, was the great the founder of surface plasmons and God knows what else. And
yes, sure.
I think it was his. Well, he was the first person I heard use it, and
Yes,
of course, it's an interesting term because it turns out that one man's aloof beam is another man's near field.
yes,
Just a question of whether the typical aloof beam working distance is maybe about 20 angstroms or something.
yes,
If you think that's a big distance, you're an electron microscopist, it's aloof. If
yes.
you're an optical microscopist, that's near
That's
field.
very
Yeah.
near indeed. Yes,
So, I mean, when Zeval came along with the PNEM technique, which is working in this same region,
yes,
PNEM means photo-induced near-field electron microscopy or something.
yes,
It's that's a different world
yes.
or a different
Yes.
perspective.
Well, it is a very English term, aloof, it seems to me. I mean, it fits quite well with certain English
Yeah,
characteristics that we both know about.
yeah,
I should just say that in that magnesium oxide slide showing these
yeah,
losses, you've got 10 nanometers, 5 nanometers, and 1 nanometer.
yeah. These are the
But
impact
these
parameters.
are the impact parameters involved
Yeah.
in this distant
Yeah.
excitation. And of course, there's a problem. It seems to me, to me, it seems that it's sort of like, a transverse flute. You're basically getting the plasmon electrons to resonate and vibrate, and you're deploying this thing which produces a broadband Fourier, frequency excitation. And but I mean, what do you mean by resolution? One of the interesting things is that the band gap scarcely plays any role whatsoever. I mean, you've got the aluminum electrons resonate, the silicon electrons resonate, the magnesium oxide electrons resonate. All you know is the total number of them that you shake and free that can oscillate in their flute, as it were. So it is it's basically a game of playing with those electrons, not worrying about the structural detail. It's a long way from thinking about work hardening.
Yeah, I agree with that. It's really a way of measuring dielectric functions,
Yes,
and
yes,
the one advance was with the work with Mike Walls, that same slide with the MgO
yes,
cube. You could actually measure both the real and imaginary
yes.
parts by comparing the aloof beam spectrum with the spectrum and the beams inside.
Sure, yes,
And actually not only get the real and imaginary parts, but get them quantitatively.
yes,
There was at that time, when it came to elastic imaging, there was still a lot of messing around. Nothing was quantitative because of the Stubbs factor.
yes,
They,
yes.
by comparison, it turned out the inelastic scattering was dead on the nail if you just took the trouble to measure the incident beam intensity.
Sure,
It was
yes.
quite interesting.
No, and of course, most of these things are done using the Kramer's Kronig.
Yeah.
You find one having looked at the other. I mean, in your discussion of this stuff, you had to deal with this quite tricky problem of a relativistic electron exciting the fields inside the crystal and then reacting to them.
Yeah.
And now I think I at one point said that you had produced a sort of a fully relativistic theory of this, and you corrected me by saying, well, it's certainly not fully relativistic, but I mean, it's a pretty tricky problem, and now very widely used, of course. And I mean, how do you, and you also gave lectures. I mean, in case people think that you spent all your life doing this sort of stuff, I should point out you were head of the department for a very long period, two periods of 7 years, and you gave lectures on relativity. So getting away from the problems of grant manipulation and stuff for the head of department. I mean, how would you teach relativity nowadays?
Well, that's a multi-barreled question. I
Yes,
think
I'm sorry. I'm
answering
sorry to be.
bits of it at a time.
Yeah,
The aloof beam work. That's thank Rufus Ritchie, like often happened, produced in his penciled notes immediately the solution with the unlikely vehicle of I think called the Hertz vector, which is not very well known, but it was
not by me.
a bit of a bump steer in a way because it turns out it's standard electromagnetism, Maxwell's theory, and the really, of course, important thing to say is that the relativity is all in this. The
Yes,
special theory is all in Maxwell's equation, as Einstein was the first to point out.
it is
And
indeed.
so the only thing you have to graft on is to make sure that you treat the electron itself relativistically when it reacts to these fields, give it the relativistic
Yes,
corrected mass and so on.
yes,
But
yes,
then the next thing you asked was about one of the duties of the head of department when I took the job was for him to give lectures on concepts in physics. You could choose whatever concepts you liked and give about 8 or so lectures, I think it was. And you could either give 8 lectures on a single thing, or I decided to give 8 lectures. I think there was probably one of them on electron microscopy and dislocations, but there were things like I gave some on chaos, and the other thing was I think I gave 2 on quantum mechanics. One of them on quantum mechanics, plumbers quantum mechanics, i.e. the toolkit, where you just solve with incredible accuracy
yes,
some of these problems.
yes,
And then the second lecture was on the mysteries of quantum mechanics, what was still unresolved stuff.
yes, sure.
And then there was one on relativity, but it was mainly general relativity. And so the book I found incredibly useful at that time was a popular book by a guy called Clifford Will, Was Einstein Right? Which starts from the fact when it was really around 1950, the general theory was really, I wouldn't say rocky, but nothing much to support it. There was the rather dubious measurements of Eddington and so on the bending of light. And then suddenly the whole thing transformed itself. Things started, lasers being fired at the moon and so on.
Sure.
And so it was a dramatic story.
Yes.
But but it was challenging to give these lectures, I must admit. I probably learned a lot more than the students.
Well, it's pretty amazing. I hadn't realized that you had covered all of that ground. Of course, these topics are all still, I mean, I still find it very hard to understand how, space-time is either a lattice, but it's definitely not. I still find that quite difficult. Where do you think, I mean, there's several things to talk about in the future. I mean, a solid state is rapidly being overtaken by biophysics of various kinds, and of course by space physics, again, of various kinds, cosmology. What do you think is the future of solid state? The old textbooks don't mention techniques very much at all. I don't think. How would you? Where do you think we're going?
I really don't have much of a view on this, because I think I would have had more of a view if I don't think in the Cavendish I ever taught a solid state physics course. I taught courses on thermodynamics for year after year. Maybe once I taught on the atomic properties of solids or something, a brief course. And so I never wrestled with a problem, which must be a savage problem now for anybody who gives solid state lectures in physics. What are you going to talk about? Which of it's an immense field, and of course, like many other fields, including electron microscopy, is being taken over by computing and machine learning, and we know that there are all sorts of people all over the place working with programs which will analyze multi-element structures and describe the minimum energies, crystallographic structure and so on, and then you have to go and sort of actually test is it actually right. But and similarly in electron microscopy, there was this tremendous boom in aloof beam imaging when after the work of Christian Kollek's group, when they brought it down into the optical region, it was a tremendous burst of energy work on that. But most of it, when you look at it, it's very impressive, but it usually shows some spectral images, and then it compares them with what you would compute. And they're, nearly indistinguishable. So you then can ask the question, why do we need what the microscopy is doing is just telling you what the structure is that you've got to then compute what is going to be the aloof beam excitation.
Which is more expensive, the computer time or the
sure,
yeah. I think it's certainly my experience of trying to teach the solid state. It was the most unsuccessful course I tried to teach. I found it almost impossible to. One of the trouble is that there seems to be very little unifying concepts to tie it together, and the ones that are really unifying somehow come to a dead end. I mean, all the quantum mechanical calculations don't tell you very much about the band gap. In fact, they get it wrong, and you can't really talk about the excited state of the crystal.
Yeah, that's a problem still.
And that's a serious problem continuing, isn't it?
Yeah.
And of course, the solid state books don't talk about the techniques, so that you still get people using the synchrotron radiation and the light factories and so on. You don't know that the electron microscope standing idle in the next room might give them the answer.
Sure.
Especially with tychography, suddenly you've got different concept of imaging altogether. There's still a lot of energy in the subject, but should it just drift and become part of material science and leave physics, or should it still be a subject in physics?
You mean solid state physics rather than
physics? Yes.
Yeah. Well, somehow or other, given that the there's still a strong tendency for university departments to remain with this old name badges, especially in the first few years. I mean, in Cambridge, for instance, there's the natural sciences set up with all these different natural science departments. There's a kind of fusion a little bit in the first year, and then in the second and third year, it all subdivides. And then simply because of lack of teaching resources in the fourth year, more recently added, they come together again a little bit.
Yeah.
Students still tend to pick up a lot of their central discipline from one or other of these places, like physics or chemistry or geology or whatever.
Yeah.
So there's still these boundaries.
Mm,
and how something develops is pretty hard to say.
It's almost impossible to see, and the politics is so difficult. I still think we should think of a much more general first year with combined science and a bit of humanity put in as well. Teaching the young men the young people how to spell seems to me still still a problem when they write their first paper. It's a bit late to be going at it at that point, but I'm sure you know that's the problem. Archie, is there anything else we should be talking about, do you think? I mean,
I think we haven't covered all of the ground, but we've covered as much as is reasonable, I think, at the time. I think we've got about burnt up the time that they're allowing us by now.
Have we burned up the time already?
Yeah, we're up to about an hour.
Yes, right. All right. I thought it was an hour and a half we had if we wanted.
Oh, well, we can go on. We'll get
I'm afraid I don't quite know what the well, the answer is I'm a bit unclear about what we're actually trying to do here. So
you had one more. I remember at one point you had one challenge for me to think of some way of we've all got bees in our bonnet at this age of our lives. And one of your bees in the bonnet is these ellipsoidal deformation zones in plastic deformation. Yes. And you were challenging me how to image this thing.
Let's go right there. I've got a couple of
several microns in size, I think, and only lasting for a microsecond.
Just about, yes.
I wasn't aware of that bit, but it did remind me of Peter Hirsch had a student, John Bailey, working on recrystallization.
Yes.
In silver, I think. And the one thing, he had a great cork-lined room to do colorimetry experiments, but he also try to observe it in the electron microscope. And the general conclusion of that was there's some kind of Sod's law that says that the recrystallization always takes place in some place you're not looking at.
Yeah,
and I think the same would be true of this thing, probably. And it made me wonder whether the thing to do, first of all, is carry out a deformation. And then at some point in the deformation where you think some of these zones will be present is give it an immense burst of radiation and freeze everything.
Yeah.
And then you've got time to study it, and you could do electron SEM backscattering or something like that, which has become a much more sophisticated technique.
I certainly think that would be the way to go. When the thing is just on the point of plasticity, it's in a state of self-organized criticality, at least I believe it is. And so it just needs a nudge to get a bit of it to be active. But it's still the fact you don't know where it's going to happen, the fact that you've got about a microsection to snatch it. I mean, I still think it has to be done with some form of synchrotron radiation. I think the electron, I don't see. The other problem that I would really like you to solve is cross-slip, I'm pretty sure, following Peter Hirsch as usual, is due to the thermally aided migration of jogs on screw dislocation. Once again, these wretched jogs, you have to go right down to a very low temperature to stop them from moving at all. And it would be so nice to see them moving along, thermally activated, to measure directly the activation energy, about 1/10 of an electron volt. And but you've got to have a microscope that enables you to see a jogged screw dislocation, high resolution to see the jogs, time to see them jumping about, let's say, once every second or so, holding the whole thing in focus, the surfaces of the film being totally
Oh,
it just seems to me, in a way, disappointingly, but also excitingly,
yeah.
beyond what you can actually see. And yet I'm sure it's true. It has to be true. There's so much evidence.
Well, following the old tradition, you would give such a difficult problem to a new research student who doesn't know that it's difficult.
Yes. At least now we have all kinds of psychological
Yeah. Oh,
comfort for them
they
available.
would need
All the qualities.
counselling.
A welfare officer. You'd have to appoint a welfare officer straight away, right? In addition to teaching him or her how to spell. That's it. Yes. Archie, what can I say? It's been
Yeah, okay, it's been a nice looking.
such a privilege. It's lovely to see you
Let's
again.
see how they manage to join the slides into this.
They've got a formidable task. Yes. Okay.
Okay, thanks very much.
Thank you.